In this lesson, we're going to look at some properties of limits that should make evaluating them a little easier. So let's look at these properties. The first set, what we call the limit laws, tell us that if I have two functions, f of x and g of x, and the limit of both exists as we get close to a, and if I have a constant c, then I can do the following. So if I'm finding the limit of the two functions added together, I can find the limits separately and add them together, right? So it's the sum property. The same is true for difference. So if I'm subtracting two functions and I want to take the limit afterwards, I can take the limit of the two functions first and subtract them. If my function is multiplied by a constant, I can find the limit of the function, then multiply it by the constant. If I have a product of two functions, I can find the limits and then multiply. And finally, if I have the quotient and I'm finding the limit, I can find the two limits and then divide them, assuming that the limit of the denominator is not 0. The power law says that if I'm taking the limit of a function taken to a power, again, I can take the limit of the function first and then take the results to a power as long as I have a positive integer. And we also know that if I have a constant, the limit of the constant as x goes to a is that constant. So the value of x obviously does not impact the value of the constant. And if I'm taking the limit of just x as x gets close to a number, I'm just going to get that number. Now, the power law combined with these two rules, let me get some other useful properties of limits. If I'm taking a limit of x to a power as x goes to a, I'm just going to get a to the n power, again, as long as n is a positive integer. The root, the nth root of x remains nth root of a as x goes to a, once again, as long as n is a positive integer, and x is in our a is in our domain. And finally, combining all of these together, if as x goes to a, nth root of the function, I can take the limit of the function first and then take the nth root of it, where n is, again, a positive integer. And if n is even, if I'm taking a square root, we assume that the function inside is positive. And finally, the direct substitution property says that if I have a polynomial or a rational function, so recall a rational function is a quotient of two polynomials, and a is in the domain of my function, then the limit of my polynomial rational function as x goes to a can be found by just plugging a into the function itself. Okay, so let's look at a couple examples. In our first example, we want to evaluate limit as x goes to 1 of cube root of 3x cubed plus 5 over 10x minus 6. So first thing we should notice that 1 is actually in the domain of this function. We could get away with actually maybe plugging 1 into this. The numerator's domain is all real numbers. I'm taking a cube root. And then if I look at the entire fraction, the only thing I got to worry about is when the denominator becomes 0, and as x gets close to 1, the denominator is getting closer and closer to 4. So, and if I plug in 1 itself in it, I don't get 0, right? So that would be, that would exclude 1 from our domain if I plugged 1 in the denominator, got 0, or if I plugged 1 into the root and I got not a real value. So what we can do then apply some of the rules that we just saw, some of the laws. I can take this fraction and apply the quotient law of limits, break this up into a limit of the numerator and the limit of the denominator, and then apply the rule we saw where I can move the limit inside of the root. And now I'm taking a limit of a couple polynomials. In the numerator, the polynomial is 3x cubed plus 5. I'm taking the limit of. In the denominator, 10x minus 6. And the direct substitution law says I can just plug in the number into these polynomials. So as x goes to 1, I can just plug in 1 into these polynomials, and the value I get is equal to the limit. So this turns into cube root of 8. 3 times 1 cubed plus 5 is 8. And on the bottom, 10 times 1 is 10 minus 6 is 4. And the last thing we need to do is just evaluate this simplify. Cube root of 8 is 2, so we get 2 over 4, and that gives me 1/2. Next example, we're going to look at the limit as h goes to 0 of h plus 5 squared minus 25 over h. Here, unlike the last example, 0 is not part of the domain of my function, and if I plug in 0 in the denominator, I'm going to get a 0. I get an undefined, right? So the denominator becomes 0. So I can't just take this limit as h goes to 0 and move it, apply it to both the top and the bottom of this fraction. So first thing we need to do is do a little bit of algebraic simplification. So we can take h plus 5 squared, expand it to h squared plus 10h plus 25 minus 25. The 25's cancel, and we'll just left with h squared plus 10h over h. And next, we can factor an h out of the numerator, and so get h times h plus 10 over h. And now, since our value gets close to 0, h is getting close to 0, but does not become 0 itself, I get to cancel the h on the top and on the bottom, right? So if h was actually 0, I wouldn't be allowed to cancel them. But since we're getting close to 0 but not reaching 0 itself, I can go ahead and cancel the two h's and be left with just the limit as h goes to 0 of h plus 10, which is again a polynomial, and our direct substitution property allows me to just plug in 0 in here and just get 10. Right, next we're going to look at a couple theorems. The first theorem tells us that a limit as x goes to a of a function f of x is equal to a value L if and only if both the left limit and the right limit give me L. Right, so as I get close to a from the left side, the value that I get should be exactly the same as the value I get as I approach a from the right side. So numbers that are slightly smaller than a and the numbers that are slightly bigger than a should give me the same answer for me to say the value of the limit is equal to L. And our next theorem says that if I have two functions and one of them is smaller than the other when I'm near a, except possibly at a itself, because we're going to look at the limit and the value of the functions at a itself is not what we're interested in. We're interested in the values near a, right? As long as both f and g have a limit, f is smaller than g when I'm near a, then the limit of f of x will also be always smaller or equal to the limit of g of x as x gets close to a. Next, we're going to look at what we call the squeeze theorem. And the squeeze theorem allows me to find a value of a value for the limit of a function where I can't necessarily work with that limit itself, but I can take that function and sandwich it between two other functions whose limits I can find. Right? So here's the statement of the squeeze theorem. It says, as long as I have a situation where I have a function g of x that is sandwiched between f of x and h of x. So g of x is bigger than or equal to f of x and smaller than or equal to h of x. whenever x is near a, except possibly a, again, because we're finding the limit, so the value at a itself is not what we're looking for. We're looking at numbers close to a. If the limit of f and h agree, right, so limit as x goes to a of f of x is equal to limit as x goes to a of h of x, both equal to some value L, then the limit as x goes to a of g of x is also L, right? So if we go back and think about it, if the limit as x goes to a of g of x is bigger or equal to L, and it's smaller than or equal to L, then it must equal to L itself. And we're going to use this in our next couple slides, where we finding some limits of trig functions that we are going to be using in our next few sections. So the first few limits we want to know are just the limits of basic trig functions. So limit of cosine of theta as theta goes to 0, right? So we are familiar with what cosine does. Here's what the graph of a cosine would look like around 0, and we can see that as x gets close to 0 from either side, cosine gets closer and closer to 1. Therefore, limit as theta goes to 0 of cosine of as theta goes to 0, cosine of theta is equal to 1. And for sine of theta, again, if I look at the graph of a sine, we see that as theta gets close to 0 from either side, the value of the function gets closer and closer to 0. So limit as theta goes to 0 of sine of theta is equal to 0. Next, we're going to look at a limit that we are going to need later on in the future sections to derive more important formulas, and that is the limit as theta goes to 0 of sine of theta over theta. Now here, once again, theta equals 0 would make the denominator of this fraction 0, so I can just go ahead and plug in 0 in here, and there isn't much of algebraic manipulation that can be done in here, so we can't really tell you what that limit is without a little bit of work. In this case, we are going to establish the squeeze theorem, establish two functions where this ratio would be sandwiched between. So this requires a little bit of geometry. Just to keep this video short, I'm not going to actually go to the geometrical reasonings for the inequalities I'm going to establish. They are in your textbook. You can go ahead and review it there. But here are the inequalities. The first one says that sine of theta is always less than or equal to theta, especially when theta is near 0. And that allows me to establish this inequality, that sine of theta divided by theta is less than or equal to 1. Right, so if sine of theta is less than or equal to theta, if I divide them, the result will be less than or equal to 1. So that's one part of the squeeze theorem, and the other part is established from this other inequality, that tangent of theta is always greater than or equal to theta when theta is near 0. And that lets me rewrite tangent as sine over cosine. And if sine over cosine is bigger than or equal to theta, that would imply that sine of theta divided by theta would be bigger than or equal to cosine, right? So cosine and theta could be switched. And that gives me the other part of my squeeze theorem. So now I know that sine of theta divided by theta is less than 1, at the same time bigger than or equal to cosine of theta. And if I take the limit as theta goes to 0, this limit of sine of theta over theta is going to be less than 1, and bigger than a limit as theta goes to 0 of cosine of theta. and we established that limit as theta goes to 0 of cosine of theta is also 1. So sine of theta over theta is less than or equal to 1 or greater than or equal to 1. And Squeeze theorem says if that's the situation that I have, if it's both less than or equal to 1 or bigger than or equal to 1, then it has to equal 1. And again, that is a limit that we're going to refer to later on in future sections. Let's look at a couple other examples. My next example, I want to find the limit as x goes to 0 of sine of 8x over 6x. Now, we just established the limit as theta goes to 0 of sine of theta over theta would be 0, except here the argument of the sine function is 8x. On the bottom, I only have 6x. So if this was also 8x, I would have the same scenario as sine of theta over theta, right? But these are not the same size. But again, here I can do a little bit of algebraic manipulation. I can remove this 6 on the bottom, make it a 1/6 sine of 8x over x. And then what I can do is multiply the top and the bottom of this fraction inside of the parentheses by 8. So I get 1/6 of 8 sine of 8x over 8x. That allows me to take this 8 that's on the top out of the parentheses and just have limit as x goes to 0 of 8 over 6 sine of 8x over 8x. We saw a property that says if I have a constant multiplied by a function, the limit constant can be taken and multiplied by the limit later. So this lets me take this 8 over 6 or reduce it to be 4 over 3 and put it outside of this limit. And now what I have here is a similar situation as we saw before. It's sine of theta over theta as theta goes to 0. Well, as x goes to 0, 8x also goes to 0. And that means this limit is going to equal to 1. So I have 4/3 over 1, and that's equal to 4/3. And one last example here. We want to find the limit as x goes to 0, 1 minus cosine x over x. And again, that is a limit that we are going to refer to in a later section. So we just want to derive it and establish its value. So here, once again, 0 makes x goes to 0 makes the denominator 0, so I can't just go ahead and plug it in. But I can do, in this case, again, a little bit of manipulation. I got to get a little creative in here. So what I'm going to do is take the top and the bottom of this fraction and multiply it by 1 plus cosine of x. Right? So 1 plus cosine of x as x goes to 0 is not 0. So I can take it and multiply it both on the top and the bottom. What that's going to do for me is take when I distribute the numerator, I get 1 minus cosine squared of x. And 1 minus cosine squared of x is a trig identity for sine squared of x. And then I'll get this scenario of sine of x over x situation, and we just establish what that value is, right? So I multiply by 1 plus cosine of x on the top, and if I distribute, so the conjugate gives me 1 minus cosine squared. Replace 1 minus cosine squared with its trig equivalent value of sine squared. And then I can take the fraction that I have and break it up into two fractions. I can take this sine squared of x and write it as sine of x times sine of x. And break up the denominator into x times 1 plus cosine of x. So I have sine of x over x multiplied by sine of x over 1 plus cosine of x. Right? So now what I can do is take this and use the property that says if I have a limit of a product of two functions, I can break that up into two limits and then evaluate these limits separately. So I know the first limit is 1. limit as theta goes to 0 of sine of theta over theta is 1. And for the second one, I can just go ahead and plug in 0 because neither of these two turn into 0. So I can take a limit as x goes to 0 of sine of x and limit as x goes to 0, 1 plus cosine of x, and use the evaluation property, and I get 0 times sine of 0 on the bottom, 1 plus cosine of 0. And that's 0 times 0 over 1, and that gives me 0. And again, that is going to be a limit that we're going to refer to in a later section.